Okay, let's get started on the homework for chapter 10. You can see I'm just clicking on it. 10 questions. Okay. So basically what they're saying is they got 20 different statistics students. And for each of them, they got their temperatures in Celsius and their head circumference. So they got their temp, and then they got their head circumference. Okay. And they found an R of 0. And then they say, does this indicate there is no association? And I'm going to go with the last one, which may be a little confusing, but there are instances where you could get a situation like this. I didn't talk about this in the homework. You could get a situation that they're related, and if they kind of offset each other, like these are going up, and then all of a sudden they kind of go back down, that'll also get you an R of 0. That's why you always have to kind of look at the graph, because this will get you an R of 0. So this is sort of what C's saying. But there are other instances, like a parabola. A parabola will give an R really close to 0. So no, there's no linear correlation. There still might be a relationship. Okay, so we're going to click on these scatter plots. Okay, so this one looks like a perfect scatter plot 5. So that should be an R of 1. Okay, so anything that's moving upward is going to be positive. Anything that's moving downward is going to be negative. So this is going to be positive and this is going to be positive. So what I'd say is, which of these two looks stronger? See if you can make that decision. Because I can see that they're both positive. Stronger, I would go with scatter plot 3. So scatter plot 3 is going to be closer to 1. Okay, now this is trending upward, but it's weak. So it's going to be away from -1 more, closer to 0. So I'm picking a positive R, closer to 1.77, and that's scatter plot 3. Click off that one. So scatter plot 3 is stronger and positive. Scatter plot 4, it's positive, but it's really weak, so 0.41. Now we have these two negatives. What I mean by negative is, see how that thing's kind of going down that way, and that's going down. So which one looks stronger? See if you could see which one looks stronger, that one or that one. The one that's more compact is stronger. And I will go with scatter plot 1. So this is going to be closer to -1. This would be closer. This R will be closer to 0. I'm not going to say it's going to be 0 exactly. It's probably going to be about this one, close to that. So I'm looking, scatter plot 1 is going to be closer to -1. And there we go. Okay, so this might be a multiple step problem. First thing we want to do is open this up and see which graph we're dealing with. I'm going to shorten this a little bit. Actually, I'll put it here so we could see them all. So they put the data in here for us. So let's go ahead and get a graph. So why don't we run it like we did with the lesson. So let's run simple linear. We won't pay any attention to this, to the numbers. We just want to see the picture. To get the picture, we do this. So looks like there, looks like that. Now it's not too linear, so we have to kind of be a little careful with this stuff. Okay. Okay, R. Here's our R right up here. When you go to 3 decimals, so this 5 is going to go to a 6. Okay, so to determine if there's a linear correlation, we want to look all the way over here at that guy right there. We want to see, is this less than or equal to alpha? And that is yes. And if that's a yes, that means that the answer to this question should be yes, there is sufficient evidence. So it's either going to be A, it's either going to be that or that. So there is sufficient evidence to claim that there's a linear. So based on these numbers, there's evidence to say that there's a linear. If you don't get that, go back and look at the lesson. So now it's like identify the part that's missing that they never talked about. So here it's saying it's linear, but if you look at this thing's obviously not linear. So that means the data is just going to do what the data does. The data doesn't look at this picture. Okay, so I guess what it's saying is even on the picture, even though the numbers say that it's linear, doesn't necessarily mean the picture is going to be linear. So, and that's that right there. So although this is saying it's linear, you always have to look at the picture. That's kind of the moral of the story. Okay, more data. Internet users award winners. So go ahead and read the question and then come back. I'm going to go ahead and run the data and take a quick look at the picture. Now there is a different way to look at the picture. You could go to graph and do scatter plot if you want, but I usually just run it because you have to run it anyway. So regression, simple linear. Always change this to the first thing and the Y to the second. We don't have to worry about anything there, just compute. Now let's take a look at what the graph looks like. Okay, so I got these 3 dots here, a dot here. So it sort of looks like this graph right here. This looks like the same thing, negative, nope, and nope. So this is definitely it. Okay, R. Hit the back button to get to the data. This is R. I copy it, paste it, and 3 decimals. Now this is pretty close to, this is, I think that was a 3, yeah, 3. Okay, now this doesn't look, it looks sort of curved a little bit, so we have to kind of pay attention to that. Okay, the null hypothesis is going to be equals to 0, and rho is not equal to 0. And I'll just kind of go over this again. Rho equals to 0 means that we're kind of expecting to see a blob with no association. What this means is that we're going to see some sort of a pattern. Okay, either up or down. Okay, the test statistic is going to be this right here. To get your test statistic, you always go to the slope row. Okay, so I'll go ahead and cut that. Paste, and we need to go to 2 decimals, so 2.44. Okay, now the p-value. The p-value is what's going to make our decision. 3 decimals, so I'm just gonna get rid of that. Okay, so now we need to make our decision. And if you did the lesson, this is sort of similar to what we did in chapter 9. But if the p-value is greater than alpha, in this case alpha is 5%. So this is true, it's going to be a fail to reject, which means we do not have evidence of linear. Okay. Not sufficient to claim that there's a linear. Perfect. So that's, we can't say with this p-value that we have enough evidence that this is a linear correlation. Okay, so that's how you do a hypothesis test through that. Okay, go ahead and read the question before you go on. Read the question, make sure you kind of understand. Okay, best actress, best actor. Now, when I look at all these, I don't see a lot of association going on. Maybe a little bit of positive here, a little bit of positive here, a little bit of negative, but these are all pretty. I don't see a lot there. I don't see a lot of correlations going on here. So regression, simple linear. Okay, make your actresses that, your actors your Y. Keep all that stuff the same, and I'll just take a quick look at the graph. See which one it looks like. So I got these 3 guys over here that look like they match these 3 with 2, so it looks like D's the answer. Okay, to find a correlation, everything else is going to be found over here. So see there's like a little bit of a negative there because it's going downward. Okay, I'm at 3 decimals again, so I'll keep the 5 there. Okay, so to run the test, this is always going to be the same. It's always going to be an equal, unless they specifically ask for a positive correlation or a negative correlation. It'll always be this. Whenever they just say correlation, let's look. A linear correlation. They don't say anything about positive or negative, so it's always going to be that. Remember, the equal means there's no correlation, and the not equal means that there is a linear correlation. So this is negative 1.28, and I got that right from here. This is going to be the same as the last problem, 0.22229. Getting that from here. Now we need to make our decision. I'm not going to write it down because it's the same one as last time. It's the same exact thing. It's greater, so there's not sufficient. We're failing to reject this. We're not rejecting this. Well, if we don't reject this, then we don't believe that. I'll write that. Maybe that'll help you. We're not rejecting this. Well, if we're not rejecting it, then we're basically taking it. Well, if we're taking it, then we don't believe this. Doesn't mean it's not true, but we don't believe it based on what we've seen. So there, and this is what this is saying. I'm just reading through this last one. Should we expect them to be the same? So what they're saying is, like, say this is one of the years they studied. Say this is like the first year. let's say the best actress was 25, do we expect the best actor to be 25? Okay, if the best actress was 30, do we expect the best actor to be 30? If this was true, if the guy's age was the same as if the girl's age was the same as the guy's age for every single year, you would get a perfect line. Like, oh, hey, there's a 70-year-old. Oh, there was a 70-year-old. It'd be a perfect line. It'd be a very strong correlation. But as you could see, this was it. There was an old. This was the actress was old, and for this case, I'm talking about like this point right here, the actor was young. So reading through these, just common sense says that they don't appear in the same movies. Okay, would you expect there to be a correlation? I wouldn't expect. Typically appear in different movies. I would say that's true. So this girl this year was probably not in the same movie as that guy, so you wouldn't expect them to be the same age. So hopefully you follow that logic. Some of this stuff is common sense. Okay, a bill and a tip. So the more the bill, the more the tip should be. The more the bill, the more the tip. So I'm looking at this. This is it, or this is it. This is a good example because you can see they're both pretty strong. The more the bill, the more the tip. That should be true. So I'm going to go ahead and run the data. Regression, simple linear, bill, tip. So compute. So see how these two are bunched up? They're not. That one like that. So it's D again. Okay, to get the linear correlation, we just go back. And that's going to be this one right here. Three decimals, that's your 3 decimals. You see this is very close to 1. Very close to 1. So this is very strong. And it's very linear just by looking at it. So what I just wrote there was that there's no association. This one is that there is a linear association. Okay, I already know that this HO is going to be rejected. Because that's you could just look and see that that's a very strong association. Okay, you can see this R. That's another indication that's a strong association. And let's go ahead and go with it. This should be big. So make sure you're looking to see where I pulled that from over here. P-value, this should be tiny. So I'm taking this over here. See, look where I'm at? Over here. Over here off to the right. Okay, so if you look at the lesson, you know if this is smaller or equal to alpha, we're going to reject. And it is. It's 5%. This value, that's 0.4%. That's 5%. There is sufficient evidence. So these are actually all. And the lesson I said, you know, not to worry about this, but you might see this stuff on a test. If everybody was to tip the same percentage, it would be a perfect increase. It would be 1. Okay, so stop and read the question and we'll pull it up. President and the opponent. Let me just see what they're measuring here. The heights. So these are their heights. So they're basically saying, hey, do you expect the height of the president, whoever they're going against, to be the same height? So I don't really have any idea. They're probably going to be somewhat the same, but who knows? Let's take a look. simple linear. Some of the stuff you can't really know until you take a look. So we're going to look at the graph. This doesn't look like I have enough data there, because that's the wrong one. Okay, this looks better. Stat. I think somehow I got off it and hit the wrong one. That's the president and his opponent. Okay, here we go. This looks better. So as the current president's height was getting taller, their opponent's was getting shorter somewhat, because that line's going down. So I have this point sitting over here and this point, so it looks like it's D again. I don't know if that's always the same, but okay, same old, same old. A little bit of a negative. We're going to go 3 decimals. So that 4 is going to go to a 5. That 4 is going to go to a 5. This is all the same. That I just wrote that there's no association. This is that there is an association. I have a hunch that this is going to be not an association. Go ahead and cut and paste 2 decimals. And my assumption was right. That's a large p-value. Large p-value is going to fail to reject. Okay. It's greater. That's 21.3%. That's 5%. 21.3% is bigger than 5%. So this means there's not sufficient evidence. It's a fail to reject. I'm going to go with this one. Just sounded right. Okay, there exists okay, so the correlation exists if somehow they're related to each other. Okay, you always want to do a scatter plot to look visually. That should always be your first step. Oh, there's more. Okay, the correlation, linear correlation coefficient measures the strength. And that's it for 10.1. Let's go do 10.2. Hope it was as much fun for you as for me. Okay, 10.2. Okay, down to 7. Now this stuff's going to be a lot of using the equation to predict. Okay, let's open this in StatCrunch. Okay, so they just give us some X's and Y's and that's it. So let's go ahead and run the data. Take a look at the picture. So linear. Once you get the data up there, you always want to take a quick look at the picture, and sort of looks like D again. Jeez Louise. A lot of D's. Okay, now to get the equation is just above that thing we were pulling before. So here we have to put the numbers in twice. So 3 decimals, of course. Now just cut and paste it. 4 needs to go to a 5. That stays, and something went wrong. Oh, 2 decimals. Great. Round the constant. That's the constant right there. A coefficient's a number that's to the left of a variable that's being multiplied to the variable. I would say there's the thing that's being ignored is this little dot up here. Hopefully that just you notice that. Oh, good. Okay, so we're back to these actresses and their ages. Okay, so let's go ahead and get the equation. Now, we don't necessarily have to look at the picture for this one, because they just asked for the equation. So here's the equation: best actor, actress. Okay, around the constant. A constant is just something that's sitting by itself. So that 3 there needs to go to a 4. And the coefficient, 3 decimals. It's going to be a rounding error. 0.211. That's right. Okay, let me go see what's wrong here. Okay, so I did it a few times and I'm a dummy. I forgot that there's a negative here. So if this is a plus, that's your number. If this is a minus, okay, if this is a, if this guy right here is a negative, you should have a negative there. Okay, so the best predicted age, 34 years old. So now they're saying, what's the, how can you predict the, sorry, what is the best actor's age as a prediction if the best actress is 34? So what we need to do is put this 34, let me write it out. We need to put this 34 into that x, so it should be 53.4. That's a minus. It's plus a minus, which is just a minus 0.211, and we're going to put a 34 in there. So I still have my calculator here from earlier, so let's do that. 53.4 minus 0.211, open parentheses, 34, and voila, 46 to the nearest whole. So that's 46. So if a best actress was 34, the actor's 46. Okay, is the result within 5 years of the actual best actor's age? It was 48. So we're looking at that one right there, 34. What was the prediction? 46. Is 46 within 5? Yes. That's all they're asking. It's 5 years or less from. Now, one thing I didn't say on that last problem, which I'll just bring up right now, is I never went and looked at the p-value, which is this one, and it still worked when it technically shouldn't have. I'll do something real quick. Oh, let me do it over here. I'm gonna get the average. I'm gonna get the average age of the guys. It's probably gonna be 46. Nope, 45. Huh. That's funny. That problem should have been wrong. Oh well. Okay, chirps. Very surprised it worked. Okay, let's go ahead and run it and get our equation. Okay, here's our equation here. 25. Okay, round the x coefficient to 4, round the constant to 2. We're doing the constant right now. So 2, that's rounded. Now I need to do this to Control C, the x coefficient to 4. And that's 4 there. And since it is positive, it's going up. Since that's a positive, that's going to be positive. Okay, what is the best predicted when a bug is chirping 3,000? So this is what I mean by when we want to look at this value right here. Since this is less than the alpha, that means we have evidence for a linear correlation, which means we're allowed to use this equation. So we need to put 3,000 into that x right there. So you just get your calculator out and plug it in. So 25 plus 0.0554, open parentheses, and we want to put 3,000 in there. Okay, so the bad thing about what we just did, if you look at all the chirps, there's none of them were anywhere near 3,000. So it's never good to make predictions outside of the data that we have. So that's called extrapolation. Okay, weight, chest size, and weight. This is so much easier than just putting it in yourself. Let's go ahead and run it. Simple linear. Let's go chest, weight. Let's compute. Now this makes sense to have a positive slope because as the chest sizes are getting bigger, the weight should increase. I know I'm missing a 1. I'm just going to add it in. I'll add in the 1. 1 decimal, keep the 3. Okay, so now what is the predicted weight for the 63 inches? So we need to take this 63 and plug it into here, as long as this p-value is less than or equal to alpha, which it is. So we're good to do it. Okay, so let's go negative 411.7 plus 14.3, open parentheses, and we want to put 63 in there. So we're predicting the weight if the bear has a chest size of 63. This comes out to be 489.2. 1 decimal, and voila. So they must have had one that was 63. Well, there wasn't, but let's see. Do you think 489 is close to 432? Some of these questions at the end are not really statistical. They're sort of common sense. So let's see how my common sense is going to go. I wouldn't say it's very close. It's exactly not. I'm going to say close. I don't know. Nope. Let's go with not very. There we go. I don't know, not that 40 pounds off. It doesn't seem to be that much on a big bear. Oh well. Okay, diameter and circumference. Okay, diameter and circumference. Okay, just a reminder, that's the diameter, and the circumference is like how big it is, around like that. So it looks like all the diameters are smaller than the circumferences all the way around. Let's get rid of my calculator and let's go ahead and pull the data up. I'm going to go ahead and run the data. So I pulled up this thing. Actually looks perfect. Just wanted to take a look because I was curious. Okay, so 5 decimals. Now there's a negative in front of this number. To be careful, I got caught on that earlier. 1, 2, 3, 4, 5. So that 1 needs to go to a 2. Okay, 5 decimals here. Missing a 3 there. 3. So 1, 2, 3, 4, 5. That 0 needs to go to a 1. And hopefully this is right. Good. Okay, predicted for a diameter. What's the best? This is a great model, by the way. Look at how high that R is. This p-value is really small, so we have to put this 35 into that X right there. Let me change the color. That 35.1 needs to go inside that X. Be multiplied here and then added over there. So we have negative 0.00552 plus 3.14171 open parentheses 35.1. So 1 decimal. So I just rounded this to a 3. Okay, this is the actual circumference. That's that. I don't think they... Okay, it's 35.1. It is beyond. $35.1 is beyond the scope of these diameters. There's none that's even close to that, so I'm gonna go with that guy. Okay, that might be it for calculations. So that's first sample. The second one's for population. This is called a regression equation. There's a lot of names for it, but okay, so that's it for chapter 10. So make sure you put in some time doing these problems and getting comfortable with them. They're going to be on test 4. And thank you for watching.